Okay, so let's talk about quantum mechanics. What I've been trying to do is, as you've seen, overlap my lectures for several reasons. One is that, lecture is always a little bit ahead of DL. Then you see the material in DL, and maybe you want to hear it again from me. So I've been trying to overlap the important concepts between the different lectures. So if some of this sounds like a repeat from last week, it's entirely intentional. And it also helps you learn and remember the material better to see it more than once. And I'd like to begin with a topic which I think is one of the most important things that you'll learn about in the whole area of quantum mechanics. And it was the motivation for developing quantum mechanics back 110, 115 years ago. And it was the fact that we could not at all use classical ideas to explain the observed photoelectric effect. Let's recall what that is. We have an evacuated tube, and on one side we have a metal plate on which we're shining visible light. And this plate is held at some voltage V. At the other end of the tube is another plate, a device for measuring the current, an ammeter, and then ground. So light is kicking electrons off this metal surface. They go to the other side. Thus, a current is flowing between the two sides, which is measured by the ammeter. Now, when I went over this last week, I went over some of it a little bit quickly. So I'd like to take a good amount of time to really understand all the features of the photoelectric effect and see why it's hard to explain with classical ideas, but requires quantum ideas instead. The first thing, and if this were the only fact about the photoelectric effect, we'd still have to throw out classical mechanics. The first thing that we see is that you don't get any current at all below some cutoff frequency. And above that frequency, the current is basically proportional to the brightness of the light shining on the plate. Now we say frequency here. We're able to make our visible light here monochromatic, maybe by using a diffraction grating or prism or something, but we can shine light of a certain color on that plate. And only when that color corresponds to the sort of blue end of the spectrum do we see electrons coming off. That's the first fact. That's totally impossible to explain with classical ideas. If in classical electromagnetism, light is just a continuous wave of energy shining on here, then electrons should come off with a range of energies no matter what the frequency of the light is. Shouldn't matter what frequency you have. There should be some electrons coming off if that's the case. But no, we see a certain cutoff frequency. Now, the other thing is that the amount of current, we can shut off the current if we crank up this voltage to high enough positive voltage. Now, if it's positive, is it attracting or repelling the electrons? We went over this last week. Because electrons are negatively charged, if this is positively charged, they attract each other. So even if the electrons are initially headed away from this plate, they get turned around and come back to that plate, and they don't reach the other side, and you don't see any current. Therefore, if you crank up the energy enough, you can find out at what voltage the current stops, and that corresponds to the energy, the kinetic energy that the electrons had when they left this plate after being hit by the light. Good enough. Now, we saw last week a more complicated plot that looks like this, that the stopping voltage depends on the frequency and is different for different metals. And we didn't take enough time, I think, to really understand how profound a observation this is. And, scientists actually mapped out this nice linear relationship between the stopping voltage and the stopping frequency, if you will, or the starting frequency for different materials, and found these nice lines. But we're completely unable to explain it using classical electromagnetism. Can we even explain what this plot means? Why does this happen? Well, you can see that as you increase the frequency, well, there's no stopping voltage at all. It doesn't take anything to stop it because there's nothing coming out until you have some critical frequency. And then as you increase the frequency of the light, the stopping voltage increases linearly as the frequency increases. I think we know how to explain that and understand it in terms of just the amount of energy it takes to liberate electrons from the surface, and then the stopping voltage corresponds to the extra energy that the electrons are carrying once they do it. So in any case, though, such behavior would be impossible to explain with classical Maxwellian electromagnetism. So it took Max Planck and then Einstein to come up with a coherent explanation of this. First, Max Planck hypothesized to explain blackbody radiation that photons are emitted that light is actually made from photons emitted and absorbed by a material one at a time. And that each photon carries an energy h times its frequency, where h is a very small number, 6.6 times 10 to the minus 34th joules seconds. Very, very small number, but the frequency of electromagnetic radiation is quite high. Still, nevertheless, you're getting very, very small numbers of joules on the order of 10 to the minus 19th, which we now know is on the scale of electron volts. So Planck's idea is that electromagnetic radiation is emitted and absorbed from atoms in these discrete quanta, or photons, one at a time. And a photon is a little wave packet. Now, Planck didn't really have a mathematical description of this thing that you see crawling across the bottom of the screen here. But later descriptions did come up with this, what we call a Gaussian wave packet. It's Gaussian in the sense that it has a smeared out position and a smeared out energy or wavelength or frequency. But it has sort of a characteristic central frequency which we associate with the energy carried by the photon. So we can say a photon has a frequency, and the frequency is about the frequency that you see here in this little picture of a wave packet. Now, the energy of a photon can be anything, as we've said. It can be anything from tiny, tiny amount for long wavelength radio waves to super high energy photons coming from cosmic rays or something like that. Photons move at the speed of light, and they are electromagnetic waves. They have an electric field that's going up and down, and a magnetic field that's going transverse to it, 90 degrees away from the electric field. And they're both transverse to the direction of the motion of the photon. If you know the direction of motion of a photon, you know that the electric field and magnetic field have to be perpendicular to that direction of motion. And it's very easy to calculate the energy of a photon, h times f, which we know that lambda times f is the speed, c, of light. So if you take h times c and convert it to electron volts and nanometers, you get 1,240 electron volt nanometers divided by the wavelength. So if you have 532 nanometer wavelength photon, you can easily divide that. Or, we'll often on final exam or something give you 620 nanometer photon. That looks all sciencey and stuff, but then you realize it's half of 1240, so you get 2 electron volts for such a photon. Or I gave you a problem last week, which I think is another even one. What was it? 310 nanometers corresponds to 4 electron volts, etc. Okay, so explaining the photoelectric effect with photons is fairly straightforward. And all the features that we see on that graph can be explained by this simple equation, that the kinetic energy of electrons coming off this metal surface when you strike it with light of a certain frequency can be measured, first of all, by E, the charge on the electron, times the stopping potential V. So EV stop is the number of electron volts that the electrons have. And that's given by the total number of electron volts the photon has. So one photon comes in, liberates one electron, but it takes a certain amount of energy, phi, the so-called work function of the metal, to do that. It takes work or energy to liberate the electron, and what's left over from that goes into the kinetic energy of the photon. That's why as you increase the frequency of the photons, you're increasing the energy of the photon. It takes more and more stopping voltage to do that. This is a perfect explanation of this and led to the Nobel Prize for Einstein, who first explained it 110 years ago.